Okay, so let's look at question 4 of the tutorial. And here we're asked to calculate the entropies, all three of them, for different processes of argon gas. Okay. And of course, argon gas is a monoatomic gas. We'll assume it's a perfect gas, whatnot. But let's just dive right in. So, for A, we're given it's an isothermal reversible expansion. And now, the moment you read the word reversible, you should associate the word reversible. So, I was reversible with the fact that reversible implies that the total entropy change will be 0. Because in other words, the universe's entropy change needs to be 0 for the process to be reversible. We need to be able to reverse whatever has happened. That also implies then that our change in the system's entropy and the entropy of our surroundings need to be the negative of each other. Right. I mean, from the law that they're the sum of each other. Okay, so let me just perhaps put in here is equal to, remember they're the sum of that, so system plus delta is surroundings implies this. Okay. So in other words, if we have a way to calculate either delta system or delta surroundings, then we have a way to calculate all these. Now, to calculate delta S surroundings, the only way that we can calculate that is if we have some information on the heat. And the only way we can get information here on the heat is perhaps if we have some information on the work and the internal energy, and the only information we have here is an isothermal expansion. So I mean, I'm thinking, okay, so then heat is negative of the work. It doesn't tell us, so it is reversible, so we can go work is nr ln Vf over Vi. I mean, that is an option. But essentially that is what we will do, because remember, in a long way, so you can go that route, or you can basically just recall that the isothermal expansion, or remember we did the isothermal expansion of a perfect gas gas the entropy change of an isothermal expansion of a perfect gas was given to us earlier in some of the notes we looked at, and it was nr ln Vf over Vi. We looked at something like that. So yeah, that's essentially what it is. Of course, this is for the system. Oops. It's of course for the system. Something else that you can also, just as a general note, so I'll put it here like on the side in green. So remember what we always have. We always have this definition for the system. We always have that is NCVM ln Vf over Vi. Oh, this is T, my apologies. Tf Ti plus nr ln Vf over Vi. You know, for expansion and heating. So we always have this general definition. But in this case, it is isothermal. So isothermal means that Tf is equal to Ti. So in other words, the ln of Tf over Ti would be the ln of 1, right? Which is 0. So what does that make this first term? That first term then becomes 0. So that's why we're left with nr ln Vf over Vi. Or, as you know it, the isothermal expansion of the entropy change for the isothermal expansion of an ideal gas. Right. Or, like I said, you can also go here, you can say, well, delta U is equal to 0, so that implies that Q is equal to minus W. We have a reversible work, so in other words, we have minus, N, R, I can't remember, T, ln, VF, something, whatever, and then you can calculate from that. You can go that whole route of stuff. But anyway, so here we have things to calculate. The work, not the work, the entropy. Yeah, so to calculate this, we just need the number of moles, which we are not given. So the number of moles is 21 gram over, what's the molar mass of argon? 39.95 grams per mole. And then 8.3145 joule per Kelvin per mole. Right, then what's our final volume? It's 460 or 4.6 cubic decimeters, so I'm just going to, anyway, over 1.2. Right, so we plug that in. And then we get 5.87 289 and a bunch of numbers. And we only have, okay, 21 is 2 significant figures. Yeah, so that's the least number of significant figures that we have. So we have 5.9 joule per Kelvin. Okay. Right. So that's what we have. All right. So that's the system's change. Of course, then our surroundings is just negative that. Minus 5.9 joule per Kelvin. Yay! Okay. It's a very nice example. Basically just hinges on the fact that you recognize for a reversible process the total entropy is 0, so then you have to calculate either delta S for the system or for the surroundings. I like to do it for the system, it's just easier. The surroundings, there's just more to calculate, so then you can easily make a mistake, but you can test it either way. You'll see you basically end up with this equation. Like write it out symbolically, then you'll see you end up with exactly this equation in the end. This is the end. Okay. Enough of that. So our next part, we need to do B. Part B. B, an isothermal irreversible expansion. Okay, so again we have isothermal expansion, irreversible expansion against P external. Okay, so it's isothermal, so in other words, against the P external of 0. So we just change a few things. So now we have an irreversible process, right? So an irreversible process implies that delta S total must be larger than 0, right? So in other words, now we can't use the argument anymore that delta S system is equal to minus, so it does not equal delta S surroundings. Okay. That is not an argument that is valid here. However, so I just need to get my my bearings. Okay, so basics. That is not something that we can do this time. But something that is useful is the fact that it's still an isothermal process, and our entropy change of our system is a state function, right? So in other words, it will not change the way it is calculated. So it will still be 5.9 joule per Kelvin. So because we would still use the same equation, the volume change will still be the same. It's irrelevant how that change happens, reversibly or irreversibly. Those changes still happen, or is still dependent on that. But now what does change is a delta S of the surroundings. And we just need to look, the formal definition of delta S for the surroundings, of course, is the heat of the surroundings over the temperature at which this takes place. But we have a isothermal process. So isothermal, because we need heat, implies that the internal energy is equal to 0. So in other words, our heat is equal to negative the work. Right. But interesting fact, this is but it's an irreversible process, and for irreversible processes, how is the work calculated? So you can write ir or whatever you want, however you want to write it. It's normally calculated as the external pressure times the volume change, right? But in this case, it will be 0 because our external pressure is 0. So what does that mean for our heat? It means our heat is also 0. So it actually means in this case the change of our surroundings, our entropy change of our surroundings, is 0. And then finally, combining these two facts, it's just equal to the 5.9 joule per Kelvin, which is larger than 0, as we would expect for an irreversible process. Right. So remember, system doesn't change, you use the same calculation, still an isothermal process. So we didn't change anything from A, that's why we use the same. So it's an isothermal, whether it's reversible or irreversible expansion, it's still an isothermal reverse. So isothermal, whatever expansion. So we use the same calculation. We didn't change the process, we just changed the reversibility or irreversibility. But it's a state function, so we can do that. Then for the surroundings, it's dependent on the heat. So we just went away, calculated the heat, but because it's against a constant external pressure of 0, the work is 0, so then all those things fall into place. All right. So our final question, which I hope alleviates most, or you remember by now, all these things that are useful. An adiabatic reversible expansion. Alright, so we have reversible. So reversible implies what? Delta S total is equal to 0. It's not an isothermal expansion, it just says an adiabatic reversible expansion. But adiabatic means something else, right? So reversible expansion, let's just first remain there for a second, means that delta S system is equal to minus delta S surroundings. Adiabatic means that our reversible heat and the heat of our system is 0. And now the entropy of our system, which is defined in principle, or by definition, as the reversible heat divided by the temperature will then be 0, right? But also, the entropy of the surroundings, which is defined as the heat of the surroundings divided by the temperature, is also 0, because there's no heat exchange with the surroundings, because it's an adiabatic process. In other words, for a adiabatic reversible process, or reversible adiabatic process, all your entropy changes will always be 0. Right. For an adiabatic irreversible process, your system change is non-zero, and your total change is non-zero, but your surrounding change will be 0, because that's the only one that's just dependent on the heat. But that's covered in the previous question, question 3. Right. But for a reversible adiabatic change, this you take it to the bank and you can cash it. So we can write reversible adiabat implies that is equal to 0. Why? Because delta S total depends on the reversibility. So delta S total is 0 because the system is reversible. The system is, entropy change is 0 because there is no heat exchange, no heat exchanged with anything. The surroundings depends solely on the heat always. So for any adiabatic change, the surrounding is always 0. But the system depends on the reversibility and the adiabatic change. Actually, I should make that more clear in the sense that for the surroundings, any adiabatic change, it's 0. The total entropy change, any reversible change, it's always 0. The system is only 0 when it's a reversible and an adiabatic change. And I mean, I've explained in the different videos exactly why these changes are 0. And then when they are non-zero, why they are non-zero. Because you have changes in the disorder which can then be rebalanced. But in these cases, you make changes to the system, but there's no changes in the disorder. In other words, your system can return to the previous state without any net balance loss in any energy. Okay, so I think that was the questions we had to do. Yeah, that was only A, B, and C. And it also gives you a nice little summary now of, you should be able to start summarizing the different entropy changes. So you know what to do for a reversible adiabat, for an irreversible adiabat, for an isothermal reversible expansion, for an isothermal irreversible expansion. Yeah, so we've covered a bunch of processes, and I think there's still one type left, which is basically the one that is just, there's nothing, or there's no controls, it just expands or whatever. Right.